All right, we're continuing on with our discussion of phase diagrams, and we're moving into chapter 5. Chapter 5 is called Simple Mixtures. We're no longer going to talk about pure substances, but mixtures of things. And it's a pretty complicated topic. There's lots of stuff in chapter 5, partial molar quantities, Gibbs-Duhem, colligative properties, activities. In the interest of time, we're only going to talk about one thing, which is the phase diagrams of binary systems. This is described in Atkins 5C, and if you pick it up there, I think you'll be okay, but it will certainly reference some things that are described in 5A earlier, so you may want to read from the beginning of the text. The main question that I want to ask is this one: how do phase diagrams of mixtures look? How do we interpret them? What do they look like, and how do we interpret them? So away we go. This is a phase diagram of a pure substance. It's really simple. Right? Pressure on the y-axis, temperature on the x-axis. I get regions where there's, say, pure gas, and on the lines there's two things present. When I have a mixture, it gets a lot more complicated because what I need to figure out is how much of a particular substance is there. What's the relative amount? For instance, I could be 90% ethanol and 10% water, or 10% ethanol and 90% water. Those two would have very different properties. And so the variable that we use to describe this composition of the system is the mole fraction, right? So it's given the symbol x sub I, right? Runs between 0 and 1. And one way you might imagine incorporating the mole fraction into these type of plots is by adding a third axis. So here's pressure versus temperature. You can imagine adding a third axis to describe the mole fraction of the system. But it's pretty complicated and difficult to interpret. So we don't do that. Instead, what we typically do is to fix one variable and to ask how the other changes with composition, right? So for instance, I have what's called a temperature composition phase diagram. What I'm plotting is the temperature versus the mole fraction of the system when the pressure is fixed at some value, right? In this case, 1 atm. If you think about this, right, what this is really telling you about is the boiling point. Right? At some point, it's going to boil, go from a liquid to a gas. And these types of phase diagrams are telling you about how the boiling point changes with composition. Conversely, I can get a pressure composition phase diagram, right, where temperature is fixed at some value. And in this case, the question you're asking is really, how does the vapor pressure change with composition? Okay, away we go. We're going to get into it. And we're going to start by talking about pressure composition diagrams. I guess I already had some notes on here. I didn't even know. So a pressure composition diagram. Right? I need you to start by imagining an ideal mixture of two volatile liquids. We'll call them A and B. So we have a mixture of these two things. And in my pressure composition diagram, then, I'm going to make a phase diagram. Pressure's on the y-axis. Mole fraction of A is on the x-axis. To be clear here, XA refers to the mole fraction in the liquid phase. So if I'm at 0, I have no XA present. If I'm at a mole fraction of 1, it's pure A. And the way you denote pure substances typically is by adding a star. So if you ever see the asterisk star, it denotes a pure compound. I'm gonna get my pen back on here. So again, if I have no A, I'm going to have no partial pressure associated with A. The question is, how does the partial pressure of the system of component A behave in between. And as you might guess, it makes a straight line. So this has a specific name. It's called Raoult's law. Raoult's law says the following, and write this in your notes. The vapor pressure of component A is equal to the mole fraction times the vapor pressure of the pure substance. It's a simple statement that the vapor pressure is proportional to the mole fraction. And so I get one type of behavior for A, because this is a mixture of two things, A and B. If I have no A present, I might imagine having pure B. And similarly, if it's 100% A, then there's going to be no B. There you go. Line gets down here. So this is the partial pressure of A. This is the partial pressure of B. The question is, what does the total pressure of the system do? And as you might guess, it does this. Just add them up. So this line here is P tot. Okay. Let me check in with you for a second. So this is that same drawing. Okay. Down here, I'm showing you some math. So this is Raoult's law. This is our partial pressure statement, Dalton's law. You can substitute in Raoult's law behavior for these PAs and PBs, do some substitution, and you end up with this equation of the line. Let me qualitatively tell you how you interpret this. If I'm at really high pressures in this system, I have liquids present. And if I'm at really low pressure in the system, I have gases present. As you might guess, when I'm on the line, you have both liquids and gases. And so let me emphasize this point to you. Imagine here I started with a 50-50 mixture of pure liquid. What would happen is you start to move down. You would move down until you hit this point. So what you're doing here is decreasing the external pressure. And as soon as you hit this point, something will start to happen. Right? Gases are now in equilibrium with these systems. The vapor pressure of the system is equal to the external pressure, right? And bubbles will form. So right at this point, bubbles, right? Because gases are forming. This line is sometimes called a bubble line, because this is where these are in equilibrium. If you continue decreasing the pressure, you will vaporize the entire system, and down here then we get pure gas, right? Still a 50-50 mixture, but it's all gas. All right, the point I want to make to you is that beyond this line, I can't have any liquids present. All right, I can do the same thing with the mole fraction in the vapor phase. Remember that the x-axis here represented the liquid phase. I might be interested in the vapor phase. And the starting point for this is Dalton's law of partial pressures. It looks very similar to what we had previously seen, YA, PA over P tot. The difference here is that YA refers to the gas phase. Okay. So you take this expression, you plug in some of your previous results for PA and P tot, and you end up with something like this. I want to pause for a second and interpret this, because I think we can actually connect with an idea that will be important later on. Here's that same equation. And what this is telling us about is the mole fraction in the vapor phase as a function of the mole fraction in the liquid phase. And what you might buy is that the composition, the mole fraction in the vapor phase will depend on the ratio of PA and PB. Right? So I get both PA and PBs in here. And specifically, the functional form or the functionality of it is shown here in this plot. This got a little cut off by my talking head, but these numbers here represent the ratio of PA star to PB star. If that ratio is 1, the vapor pressures of the two components are equal. If that number is 2, we're saying that the vapor pressure of A is twice as big as the vapor pressure of B. And this is where this gets important. Right? Imagine I have a 50-50 mixture of some liquid. Right? If the vapor pressures are equal, you can imagine doing that Raoult's law plot, but the mole fraction in the gas phase has to be exactly what it is in the liquid phase. It's sort of a simple consequence of the fact that these are identical. However, if the vapor pressure of pure A is greater than B, right? Imagine it's twice as big, what you will find is that although the liquid is 50% A, the vapor is 65% A. Right? It's bigger. And so what this is telling us is that the vapor is enriched in the more volatile component. Right? The partial pressure of A is twice as big as B, it's more volatile. And so this plot is exemplifying or demonstrating something that you know from organic chemistry. This is a really helpful flag to kind of keep in the ground and make sure you're doing these things right as we move on. And I'll reference this later. At any rate, going back to that derivation, I can take this expression for the mole fraction in the vapor phase. I solve it for XA, and you end up with this. And then you take that result and you plug it into this expression and simplify it, and you end up with something that looks like this. Okay. If you're a note-taking person, write this in your notes and circle it. Right? This guy here. This is telling me how the total pressure depends on the mole fraction in the gas phase. And let me show you what these plots look like. Again, we're going to plot P versus YA. Here's 0 and 1. Here's PB star. Here's PA star. And what you'll see is that, unlike Raoult's law, this is not linear. YA is in the denominator of this expression. So on this plot, it will end up looking like this. Imagine it connecting. All right, let me interpret this a bit for you. Again, down here, gases, low pressures. High pressures, we have liquids. Previously, we had the bubble line, right? The spot where bubbles would begin to form. This also has a name. It's called the dew line. Here's the idea. Again, if I had a 50-50 mixture and I started pressurizing it, so this is a 50-50 mix of pure gas. As you increase the pressure, the system will increase pressure, increase pressure, increase pressure until you hit this point right here. Once you hit that line, you get the first drop of liquid, the first bit of dew. Keep increasing the pressure, it will liquefy, 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 liquefy. If you increase it more, right, you end up now with pure liquid. So again, the point that I want to make to you is that gases down here, liquids up here, and above this line, there are no gases which are stable. One last point. I've talked about the liquid phase and the gas phase separate, but in fact, you can combine them onto one plot. So I can put XA and YA on the same axis, and it looks like this. Pressure versus the overall composition. We usually call this Z sub A. Again, above the black line, we have liquids, and there are no liquids anywhere below the black line. Below the purple line, I have gases, and above it, there are no gases which are stable. And this begs a really interesting question. I have liquids here, and I have gases here. What exists in this region? Don't know. You'll have to tune into the next video to find out. All right, hope to see you soon, and talk to you later.